Welcome to the pre-lecture for Class 22, where we will be talking more about local stability analysis. Now, remember the brief summary of what we've done so far. If we have an autonomous differential equation system, x prime equals f of x, we are going to locate the equilibrium points by setting the right-hand side to 0, and then we linearize the nonlinear equations about each equilibrium point, where essentially we are taking the first two terms of the Taylor series expansion. And we noted that since we searched for the equilibrium point, this first term in the Taylor series expansion is simply going to be 0. This is the Jacobian evaluated at the equilibrium point, and we use the eigenvalues of that Jacobian to determine the stability and type of the equilibrium point that we have, if possible. Now we can combine local stability analysis with information about nullines and direction fields to estimate the phase portrait and determine the qualitative behavior of the differential equations. On the next page, we have some optional information about the multivariable Taylor series expansion. For those who are interested, the multivariate version of the Taylor theorem is written out here. There's a citation. You can go find more at this nice Wikipedia site. And this does relate to what we've been doing for our analysis. Let's go to the next page to talk about some questions. Why do we linearize only around the equilibrium points? Well, again, here we have our Taylor series expansion, and we note that if our x is not an equilibrium point, then this value, f of that x, is not going to be 0. And if f at that x is non-zero, that means this term is going to dominate over the linear term. So now it's clear why we need the first term to be 0, but why do we ignore the quadratic or the second order terms in the Taylor series? Well, if we are close to our equilibrium point, that means this distance is small, and that allows the linear term to dominate the higher order terms, because this distance, which is small, less than 1, is going to be larger than the distance squared and all other higher powers. Practically speaking, we could include higher order terms if we wanted to, but it does turn out that dealing with nonlinear terms makes analysis a lot more tricky, and the payoff is not necessarily worth it. Now, for those who are curious, you've probably heard reference to the idea of a nonlinear system being linearizable. And there's some information here for you to take a look at to explain that a little more in depth. Now, remember that this local linearization only works if the real part of the eigenvalues of the associated Jacobian are non-zero. In class, we're going to work through an example of the nonlinear pendulum. But for now, skip to part 2 of the notes to see how to handle the case when the real part is 0. We are going to continue to use the example of the nonlinear pendulum, which, by the way, in case you would like a refresher, was derived in lecture 14 of this class. Since this is a second order ordinary differential equation, we can actually write it as a system of first order differential equations, something we've practiced quite a bit. Remember that the constant c is the scaling of our damping term. If there is no damping, that means physically we have a pendulum that continues to swing, and we will in fact get purely imaginary eigenvalues of the linearized system. Purely imaginary eigenvalues in a linear world means that there is a center at the equilibrium point 0, 0. However, Hartman-Grobman does not allow us to infer that the nonlinear system also has a center there. So what do? Well, we still have physical intuition that when there is no damping, the pendulum is going to swing periodically and indefinitely. How can we prove this mathematically? When we derived the ordinary differential equation in the case of no damping, we made use of conservation of energy. Remember, total energy is kinetic energy plus potential energy, and in this case, conservation of energy means this is going to be constant. Now, for the sake of having our differential equations to reference, I will write them down here. Our energy function, a function of angular position and angular velocity, was derived in lecture 14, where m is the mass and capital L is the length of the pendulum. Now we would like to confirm that the derivative of this energy function is in fact constant if we have conservation. Pause the video and take the derivative and confirm for yourself that dE by dt is in fact 0. Here is the result of taking the derivative. Remember that the derivative of theta is omega, and when we sum everything together, we do show that the derivative of the energy is in fact 0. Let's go to the next page to see what this implies. The derivative of the energy is 0, there's no damping. That means that the energy at any time is actually going to be the energy at initial time. So where we start at time t naught is where we're going to stay with respect to energy as time advances toward infinity. What this means geometrically is that in the phase plane, solution trajectories are actually going to be level curves of the energy function. You're going to see this on a homework example as well. For now, let's see what this means through an example. Let's suppose that our angular displacement at time 0 is pi over 3, and our initial velocity at time 0 is going to be 0. That means we're going to release the pendulum from rest at 60 degrees. Using the equation for the energy, we can see what it is at time 0, which reduces to -1/2 mass times gravity times length. Since the derivative of the energy is 0, though, that means the energy is constant. And so when we evaluate the energy at any time t, we are going to have the same value. The energy at any time t then is going to be -1/2 mass gravity length. What is this doing geometrically? This is describing the solution orbit in phase space. So if we have a particular path that starts at pi over 3, 0, the fact that the energy is constant shows that we have a closed loop. Let's look at this a little bit more in higher dimensions. Let's take a look at this point here. This is the origin 0, 0. Here we have a saddle point, and the bottom of each one of these bowls is a stable equilibrium point. Now think of the energy function as overlaid on top of the phase portrait of the solution trajectories, where each trajectory must have a constant energy value. Along any one of these solution trajectories, the energy function E is going to be constant. Now, near the origin then, the level curves of the energy function are closed loops. This tells us that 0, 0 is in fact a neutrally stable center. So this is a case where the linearized version actually does match the nonlinear system from which it came. Let's go to the next page. In the case of no damping, the nonlinear pendulum equations form a conservative system. Let's define the integral or integral of motion or first integral. That will be a non-constant function, capital K, a function of our ODE solution vector x, such that the total derivative of K equals 0. Let's think about this in 2 dimensions. Suppose, for example, that we have our 2-dimensional function x with entries x and y. Then our integral K is a function that is constant along each solution orbit. In other words, K is a function whose level sets are solution orbits of the ODE. Now, in the case of an autonomous system of differential equations, that differential equation is considered conservative if it has an integral. In other words, if such a function K exists for that ODE. So, for example, the nonlinear pendulum that we've been looking at is conservative when there is no damping, because we have exactly found an integral function. It's the energy function. The energy function serves as an integral for the no damping nonlinear pendulum system. But even in the case where there is damping, it turns out that the energy function can still be useful to us. Why is that? If we take the time derivative of the energy function and keep non-zero damping in here, we find that the derivative of the energy function is negative, meaning we are seeing a decrease. So this implies that when there is positive damping, energy will be decreasing over time, which makes physical sense to us. What does that mean for the solution trajectories? The solution trajectories will asymptotically approach one of the minima of the energy function, and that is where the stable equilibrium points of the system are. Now, this is all great when we have some physical intuition. It turns out, though, we can extend this idea even when we don't have specific physical intuition. Let's go to the next page. So even when there's not a clear sense of energy, we can generalize this idea to many other ordinary differential equation systems through what are known as Lyapunov functions. A Lyapunov function is a scalar function, meaning it has a scalar value that is used to tell us something about the stability of an equilibrium point. So the energy function for the nonlinear pendulum is also an example of a Lyapunov function. Now, I'll tell you in advance that finding a Lyapunov function in practice can be challenging, but we are going to get some practice. Before we look at this example, a Lyapunov function for a 2D ordinary differential equation system is essentially going to look like some kind of bowl in 3 dimensions. We generally name the Lyapunov function V, and this function V usually is created so that the solution curves of the associated ODE are embedded in the sides of that bowl. So if we assume that our equilibrium point is 0, 0, then our function V is going to be a function of the solutions of the ODE with the following requirements. V must be positive near the equilibrium point 0, 0. It must equal 0 right on the equilibrium point, and the time derivative of V itself must be either always negative or always positive. Why is that geometrically the case? Again, thinking in terms of our energy function, suppose we have any function V that is bowl-shaped with the solution trajectories embedded in it. Suppose that the solution trajectories are spiraling down toward the equilibrium point. We should be able to show then that the derivative of V is in fact negative. Let's take a look at this example. X prime is y plus x cubed. Y prime is minus 2x. This system has only one equilibrium point at the origin, and the linearized system does have purely imaginary eigenvalues, so we can't use our standard local stability analysis to determine the nature of the equilibrium point. But notice something. If we multiply the first equation by x and the second equation by y and add them in a clever way, we get the following equation. And that equation is actually the derivative of x squared plus y squared over 2. What is useful about this equation? It's always positive for non-zero x. So we've found a function that is changing in time, always increasing, which suggests that we could possibly use this to define the Lyapunov function. So the integral of that function is going to be our Lyapunov function, x squared plus y over 2. That function has level curves that are ellipses centered at the origin. Now note that this function v is also positive for any xy that is not the origin, and it is 0 at the origin. We also know, the way we've chosen v, that its derivative is always going to be greater than or equal to 0. So, since the derivative of v is always greater than or equal to 0, that means that trajectories near the origin are going to be continually moving away from the origin, making the origin an unstable equilibrium point in this case. So the picture with an unstable equilibrium point will have trajectories spiraling away from the origin. Let's go to the next page. In summary, we actually now have found 2 different tools to help us determine the stability of equilibrium points. Our friendly local stability analysis, which is a fairly mechanical process. You only have to find the Jacobian and plug in the values of the equilibrium points, determine eigenvalues, and you've got your stability information. The only issue is that as long as the eigenvalues of the Jacobian do not have zero real part, we can use this. But if they do have zero real part, we have to go to something else. And that something else is a Lyapunov function. And as we discussed, energy is often a good candidate for choosing a Lyapunov function, but we will also discuss other ways of choosing it after we've practiced using these Lyapunov functions for a little bit. In class, we're going to get a chance to practice some more. See you then. Here's a bonus summary of the requirements for a function to be a Lyapunov function.